Provisioning GPU clusters should feel like spinning up a web app, not like rebuilding an entire data center. Even today, standing up a production grade cluster still involves juggling instance creation, SSH keys, GPU drivers, monitoring agents, log collection, and that's just to get to a baseline. That's exactly the friction we are eliminating here. Hello everyone, I'm Sanskriti Harmukh, a developer relations at Vultr, and in today's Tech Talk, we will show you how Vultr Open Cluster Manager can turn a single node to a fully bootstrapped GPU cluster with Slum scheduling, Prometheus metrics, and Grafana dashboard all provisioned with no manual config. We'll break down what makes this possible, how it works under the hood, and we'll wrap it all up with a live demo that proves that the system works as promised. So, without any further ado, let's jump right into it. Vultr Open Cluster Manager is a turnkey solution to deploy GPU backed compute clusters without having to configure them manually. With just a single node, it bootstraps a full cluster. It is designed to translate user intent into real functioning infrastructure. This includes network setup, user configuration, monitoring endpoints, and workload schedulers. Instead of stitching everything together from scratch, Vultr Open Cluster Manager automates the entire life cycle from node provisioning to live dashboards so you are ready to deploy workloads out of the box. This is especially useful for ML training, HPC workloads, or research pipelines where time to readiness and visibility to system health are critical. Let's take a closer look at what's running behind the scenes. At the infrastructure layer, Terraform provisions worker nodes, provide host names, configure networking, and leverages Vultr API to dynamically create instances as needed. Once these machines are operational, Cloud Init and Ansible handles the configuration. Cloud Init performs one-time bootstrapping tasks like installing essential base packages, while Ansible applies consistent and version-controlled configuration like SSH deployments, disk mounting, and driver installation. Moving on to the cluster runtime, Slum orchestrates job scheduling, manages GPU resource allocation, and maintains node state information. It serves as a central coordinator for workload management within the cluster. Additionally, SSH access is available across all nodes, allowing secure remote administration. Finally, the observability layer provides monitoring and logging capabilities. Each node runs exporters, for example, DCGM for GPU metrics, that feed data into Prometheus. Pre-configured Grafana dashboard offers real-time visualization, while Loki aggregates log for full-stack visibility. This end-to-end observability is delivered out of the box, while eliminating the need for manual YAML configuration or troubleshooting port conflicts. Next is the diagram that shows how everything connects. At the core is the manager node, which serves as a control plane. It orchestrates the entire cluster lifecycle by running Terraform to provision infrastructure, Ansible to configure instances, and initiating the cluster bootstrapping process. The worker nodes are GPU-enabled instances that register with Slum Workload Manager. They continuously report GPU metrics such as utilization, temperature, memory pressure through NVIDIA's DCGM exporter and node exporter. These metrics are collected and scraped by Prometheus. Prometheus aggregates metrics, feeds them into Grafana, which automatically loads dashboard displaying detailed per node and per GPU statistics in real time. In addition to metrics, system logs, job execution logs, and boot diagnostics are collected and forwarded to Loki, providing a centralized and searchable log repository. This enables efficient troubleshooting and insight into workload behavior over time. Let's now jump into a live demo. We'll start with a manager node and then trigger provisioning of GPU worker nodes. Once these nodes are active, we'll explore Prometheus targets and ensure that metrics are being scraped. Finally, we'll log into Grafana, navigate to the pre-built dashboards, and observe live GPU telemetry. Before we begin, let's quickly cover the prerequisites for deploying Vultr Open Cluster Manager. First, you'll need a Vultr API key with sufficient permissions to create resources such as Vultr Cloud Compute instances, SSH keys, and VPCs. You can generate this from the API section present under your Vultr account settings in the Vultr Customer portal. One thing to note here is that if you're deploying Vultr Open Cluster Manager on dynamically assigned IPs, then your Vultr API's access control list must allow requests from all IPs to ensure that user space tools can access the Vultr API. But if you're using Vultr reserved IPs, then only that specific IP address need to be added to the access control list. Optionally, you can enable a centralized logging by integrating Loki. For that, make sure you have the required credentials ready. This includes a base URL of your Loki instance and a basic auth username and password. These values are configured as environment variables during deployment. In this demo, I have a Loki container running behind an Nginx proxy, which adds basic authentication. Any Loki instance reachable by cluster nodes, whether local or remote, proxied or direct, work as long as the nodes can access the provided URL and authenticate successfully. To kick off the demo, let's start by provisioning the manager node. For that, navigate to the compute section in the Vultr customer portal and click on deploy server. Vultr Open Cluster Manager need not to be deployed on a GPU instance. Therefore, you can select a non-GPU compute type. For example, here we'll go with shared CPU. Next, choose a region where the desired GPU instance plan has available inventory. This is essential because the Vultr Open Cluster Manager will attempt to provision VPC resources and spin up GPU nodes in the same region. Then pick a compute plan based on your resource requirements. Next, we have one of the most important part of this setup. Navigate to the marketplace apps here and search for Vultr Open Cluster Manager. Select the application and fill in the required fields. Once the value is provided, select an SSH key for secure remote access. Optionally, you can configure a startup script or attach a firewall group if needed. Then provide a label to your manager node. Once everything is configured, click on deploy. This action will launch a Vultr Cloud Compute instance with Vultr Open Cluster Manager installed and pre-configured. Now that our manager node is up and running, let's SSH into the environment to execute the rest of the steps. We have now successfully connected to the manager node remotely. As you can see, at the root level, we have several files and directories relevant to the deployment. We'll use the simplified flow, which involves verifying the configuration and running build cluster script. But if you prefer more control or want to manually walk through the provisioning and configuration, then you can execute Terraform and Ansible playbook separately. For that, refer to the supporting documentation linked in the description below. Let's start by inspecting the core configuration file that drives our cluster setup. This file is divided into two main sections. First one is the Terraform configuration. This section defines the foundational infrastructure for our GPU cluster. Instance plan here specifies the exact Vultr GPU instance SKU you want to deploy. In this case, we are targeting a powerful instance equipped with an NVIDIA L40S GPU with 16 CPU cores, 180 GB RAM and 48 GB of VRAM. Choosing the right plan here ensures that your cluster nodes have the necessary compute and GPU resources for your workloads. Instance GPU and instance GPU count indicates the GPU model and number of GPUs to attach per instance. For example, setting instance GPU to L40S and instance GPU count to 1 means each node gets one L40S GPU. OS ID determines the operating system image deployed on each node. The ID 1743 corresponds to Ubuntu 22.04 LTS, which is a stable Linux distribution suitable for GPU workloads. Instance count specifies how many nodes will be created in the cluster. Instance region sets the geographic location for your worker nodes. This is same as the region where your manager node is deployed. VPC IDs is the identifier for the virtual private cloud network your cluster nodes will join, enabling private and secure communication between them. And if you have a firewall group configured, you can supply the ID here for network security. This variable, on the other hand, expects a list of SSH key IDs to be injected into your nodes for secure and passwordless access. Host prefix and host suffix control the naming pattern for each node, helping you easily identify them in the network and management interfaces. The second section is Ansible configuration. Once the infrastructure is provisioned, this section guides the automated software setup on your GPU nodes. Loki cluster URL, tenant username, and tenant password are used to configure Loki, enabling you to aggregate logs from all nodes for easy monitoring and troubleshooting. Alongside Loki, Ansible playbook also installs Grafana Alloy and Slum. You can customize these variables to go with your existing logging and monitoring solutions. With configurations reviewed and adjusted to your needs, you can launch the full deployment by running the build cluster script. This script handles everything from start to finish. It calls Terraform to spin up the specified GPU instances, network settings, and related infrastructure. It also runs Ansible playbooks to install the necessary software component, set up logging, monitoring, and job scheduling. Once complete, it outputs a URL to access your Grafana dashboard where you can visualize cluster health and GPU metrics in real time. If any step fails or encounter transient issues, then simply rerun the script. It is designed to be idempotent, meaning it will skip successfully completed steps and retry only the ones that need attention. Before heading to the Grafana dashboard, let's verify that Prometheus is actively scraping metrics from all registered endpoints. To do that, open a fresh browser tab and navigate to the Prometheus targets page, which is usually accessible at port 9090 under targets path of your manager node's IP. Here you'll see a list of all registered scrape targets, including node exporter endpoints for system metrics and DCGM exporter endpoints for GPU metrics. Each target should show a green up status. This confirms that Prometheus is able to collect metrics from all expected sources in your cluster. Now that the cluster is deployed and we have also verified that Prometheus is actively scraping metrics from the required targets, it's time to visualize those insights. For that, open the overview page of your manager node, scroll down and locate the Grafana dashboard link and credentials. Let's navigate and log into it. Now you will have access to the performance and usage metrics for your cluster. You can build custom dashboards using Prometheus as your data source and monitor logs via Loki. Let's explore the pre-built dashboards. The Node Exporter dashboard provides comprehensive system-level metrics including CPU utilization, memory consumption, disk input-output, and network activity for each cluster nodes. It helps monitor the overall health and performance of all compute instances, whereas the NVIDIA DCGM Exporter dashboard focuses specifically on GPU metrics, offering real-time insights into GPU utilization, memory usage, temperature, and other critical hardware statistics across all GPU nodes in your cluster. Now, if you want to scale the cluster, simply open config.yaml, increase the instance count, save the changes and exit from the file, and then rerun build cluster script. Now Terraform will handle the provisioning and Ansible will configure the additional nodes automatically. And that's how in just a few steps you can build a GPU ready, fully observable and scalable cluster using Vultr Open Cluster Manager. To summarize, Vultr Open Cluster Manager abstracts away the operational complexity of standing up GPU clusters. With built-in automation across provisioning, configuration and observability, it provides repeatable, production-grade foundation for compute-heavy workloads. To replicate this setup on your end, you can deploy it directly from Vultr Marketplace application, customize it based on your needs, and scale horizontally as demand grows. Get started at Vultr today by claiming $250 in free credits on a new account using the promo link attached in the description below. Additionally, start engaging with Vultr community by signing in to the Vultr community forum, whose link is also available in the description. This is the place where you can connect, share ideas, and seek help from Vultr team and fellow infrastructure engineers. Thank you so much for joining us. We hope this session helped you build scalable and efficient GPU clusters at ease.